Assalamu alaikum. Let us wait for people to join in. Walaikum assalam. Walaikum assalam. So today we are going to start a new topic, and that's a very interesting topic because this is where the real digital signal processing is. It is about the implementation part of the signal processing, and so I'm just waiting for people to join. So there are three components of signal processing, or this course, so to say. One is about the representation, and analysis. Okay, one is this part. The second part, which we just covered, is implementation. This is the second part. Okay, so let's draw this line. So from representation and analysis, we learned about implementation, how you implement a signal processing system. The third part is the design part. So this is the part that we are going to learn today. Okay, so in the representation part, if you remember, first we said a signal is represented as a weighted, shifted summation of impulses. So this is our primarily the representation part. Then analysis part is where you can analyze a signal or a system, and we learned about discrete time Fourier transform, DTFT, discrete time Fourier transform. Why? Because sometimes there are things which are not visible, which are not vivid in time representation of a signal, and you want to see something, you're looking for something, and you go and do the transformation. It is almost same as sometimes if you want to look for something, you take x-rays or MRIs, or specific, for example, a test in corona, that if they want to find out whether coronavirus is present, they take a test, and that test will basically enable them. Just looking at the face of a person, sometimes it is difficult to figure out what is happening to him. So you sometimes want to see something very special in the signal, and for that you take transformation. In this course we have learned only one transformation, that is discrete time Fourier transform. But then there are others like wavelet transform, curvelet transform, homomorphic transformations, and there are many. And people have devised them because they want to see a specific thing in the signal, so they transform a signal from time domain to another domain. At least we know that transformations are important. Discrete time Fourier transform, and this will also lead us, which we have not covered yet, discrete Fourier transform, and that will lead us to fast Fourier transform. And these are the things that we are going to learn in a while. And in the analysis part of a system, we have learned about Z transform, and we know the importance of Z transform. That Z transform basically helps us to to figure out whether a system is stable or not. So Z transform has its own importance, that for a causal IIR system, all the poles must be inside the unit circle. So this is what we have covered. And then we came to the implementation part. And implementation, we said important that you now have designed a system, and because in this course we are only focusing on linear and time invariant system, so our systems are either FIR system or IIR system, finite impulse response or infinite impulse response. And then we find out that people have figured out interesting way of implementing what looked like just a difference equation. And we started about direct form 1, then we started about direct form 2, then we studied about transpose direct form 1, then we studied about transpose direct form 2. Okay, and we also studied that for FIR filter there is no transpose direct form 1 and 2 because there is no recursive part, so there is only direct form and transpose form. And then we went through understanding the sensitivities of a system that is to be implemented on an embedded platform, which is only has a processor which may be a 16-bit processor or maybe a 24-bit processor. And MATLAB basically design everything into 64-bit double precision arithmetic. So MATLAB is never used in any embedded system. It's like usually you have to code your algorithm in C or maybe C++, usually in C, or sometimes even in assembly language or in Verilog. And believe me, if you keep working as a computer engineer and you are working on embedded systems and signal processing system, may they be electromedical equipment, or they may be entertainment or games or artificial the deep learning platforms or whatever, it's only like 5% of the people would actually develop algorithms, and 95% will be employed implementing an algorithm. So that is why it is important for you to understand that 64-bit is not the luxury you have as an implementation engineer. You got to curtail it to 16-bit or 24-bit, and if it is a custom hardware that you are designing, then it is up to you. You need to decide the best width for your algorithm. It may be 17 or 18-bit or 14-bit, and so we spend a lot of time learning about the quantization, that how quantization affect the system response, how quantization affect the stability of a system, and just spend a lot of time. And you got also a lab where we learned about this. Now we are moving towards the third part and the last part, but we'll come back and learn fast Fourier transform. This is almost the last part. As I mentioned, DFT and FFT are still to be covered. The design, that how you design a signal processing system. And because in this course we are only focusing on system, means an FIR system or an IER system. So once we say design is an FIR system or an IER system. Either you design an FIR system and an IER system, and you have been designing these systems, and you are using MATLAB toolbox, filter design toolbox, FDT toolbox in MATLAB to design any kind of filters. But now we need to really understand that how these things are designed, and that will also help you to understand the design problem in general in signal processing. And design problem again is not specific to just designing an FIR and IR system. Sometimes you have to design different types of algorithms, but this will help you to comprehend and understand that how signal processing algorithms are designed. So let's come back and focus our attention on either designing an infinite impulse response or a finite impulse response system. Okay, so once you say it is just a LTI, so we constrained ourselves to design a frequency selective filter. And as we know that a frequency selective filter is a filter that either will pass, so if it is a digital filter, so we know that the maximum frequency you can have is pi. Okay, so and because usually once you are designing, you want to look at things in frequency domain, not in time domain. Okay, so frequency domain would tell you that these are the frequency you want to let pass and these are the frequencies you want to stop, and you don't plot it from -pi to pi because you know it is symmetric. Your spectrum is a symmetric spectrum, the magnitude of the spectrum, so you only need to vary from 0 to pi. And pi, from our sampling chapter, we know this is fs over 2. Pi corresponds to half of the sampling frequency, and this is the maximum frequency content that you can bring into your system as a digital signal or a system. So the first type is low pass. Low pass is something like this. This is a low pass system. Okay, you want to let pass the frequencies in your signal going from 0 to omega c. So omega c is the cutoff frequency, and after that you want no frequency to get through the system. So you want to filter out all these frequencies. This is called filtering. So you filter out all the frequencies here. So this is called a low pass filter, and it is our exponential j omega. So we are looking in frequency domain. So this is a low pass filter. Okay. The second one is a band pass filter, where you let a band of frequencies to pass. Okay, we are planning a project for you, for your final term project. We'll give you a project where you will design these different types of filters. So you have omega p1 and omega p2. So you want all the frequency contents between omega p1, omega p2 to pass through it, and then you want to stop rest of the frequencies in your signal not to go through the system. So you clean up. And usually band pass filters are used if you have multiple channels and you only want to watch one, like you want to watch CNN. So you have a filter which will only let pass the CNN signal to go through, and rest all channel will be filtered out. So the third type of system is called the high pass. As I told you earlier, that highest frequency content in our signal is pi. So pi is the highest frequency. So you have omega p, which is you pass from 2 to pi, and rest you filter out everything. And then there are other type of filters as well. A notch filter, for example. A notch filter is a filter that will only stop one frequency from entering into the system. Right? It will only stop this frequency. So this is the frequency you hate to be in your signal, and you want to pass this frequency. And usually this is in the medical equipment. It catches the electricity. From the electricity, it catches a 50 hertz or a 60 hertz sinusoid. Every medical equipment, ECG machines would actually get induced this particular sinusoid, and you got to remove this. So if you are only interested in removing one frequency, so you use a notch filter. And then there are other types, like you only want to stop a band of frequencies, and you want other to let pass through this. So you can almost draw anything which you want to pass and the other which you want to stop, and it will have a name. So this is a band pass filter, and this is a high pass filter, where the maximum frequency content in a digital signal is pi, not infinity. So pi is the highest frequency, so this becomes a high pass filter because you want to pass this frequency. Now the issue is, though it would be very nice if we could actually design a filter which would just let or allow some frequencies to pass, the other to stop, our life would be very easy. So engineering, as I told you, starts where you cannot actually accomplish these things, which is called ideal system, where ideal is not possible. And the engineering starts where ideal is not possible. So ideal is not possible. There's absolutely no way for you to let pass all the frequencies, your frequency response to remain 1, and then all of a sudden it drops down to 0, and then it remains 0. This is not possible in reality. In reality, what is possible, that you got to constrain this. You cannot get this 1, you cannot this as omega cutoff. It is not possible for a system to be an ideal system. So you got to compromise. And once you compromise, you say, okay, I will allow my frequency response to live in a region, in this region. And you want this to be very, very small. You want to make this very small, but you got to give it a little space for the frequency response to go up and down across this one. Okay, and how tight you want to make it, that depends on how much you are willing to invest into your system. So you allow it a little deviation, which is called a sigma or a sigma 1, and these are called the pass band, where you want the frequencies to pass. This is called pass band, and this delta 1 is called pass band ripple. So you allow some ripples to happen here. So now your frequency, your response will be going up and down like this. Okay, so it won't be just one, because one is not possible. This is ideal, is not possible. So you allow something. And delta 1 usually is very, very small number. It may be delta 1 is, for example, 0.01. Yeah, so very small number that you basically allow a little variation. What does it mean? That instead of the frequencies which you are passing, they remain as they are, they may get a little gain. Some of them get a little gain, some of them get a little attenuation. Okay, and you say, I don't mind my frequencies, the wanted frequencies, to change a little in their magnitude, a little in their magnitude. And then there is absolutely no way for the frequency response to drop down to zero. It is not possible. So you got to give it a space where it can go and die. So dying back to your frequencies to go back to zero is not possible. So you allow them a region of transition. This is a transition to happen. So this area is called your transition band. Okay, so this is where you want frequencies, this is where you stop these frequencies. And you want it to be very, very narrow, but it depends. As you start basically changing your constraint for it to be narrower, it becomes more expansive filter to have. So it's up to us whether we want what transition band we want while we are designing a filter. Okay, it means that you wanted frequencies till omega c, but some of these frequencies will get attenuated. Okay, you got to do this compromise, and these are unwanted frequencies after omega c. So you let these frequencies to have like a magnitude, still they will get into your system. So the best thing is that you let the user not to use a band of frequencies, and this is called a guard band.